dead. Everything. Gone. 66 million years ago. One really bad Tuesday. And almost everything alive on Earth just stopped. Whoa. But here's what's wild. We know this. We know it happened. We know roughly when, roughly how, and we even know what the last few weeks probably felt like for a T-Rex standing in what is now Montana. And we figured all of this out without a single witness. Without a video. Without even a note. We figured it out from rocks. That's paleontology. And if you think it's just nerds dusting off bones in the desert, hold on. Because what these people actually do is more like CSI crossed with time travel, crossed with the most humbling existential crisis you've ever had on a Tuesday afternoon. So, how do you investigate a crime scene that's 100 million years old? N? Where do you even start? N. You start with death. Specifically, you start with the weirdest, most specific kind of death, the kind that leaves a copy of itself behind. Okay, so picture this. You're a dinosaur. Rough day. You die near a river. Your body hits the sediment, the mud and sand at the bottom, and here's where something incredibly rare has to happen. Normally, your body just decomposes. Bacteria eat you. Scavengers eat you. Time eats you. You're gone in months. No trace. Nothing. That's what happens to 99.9% of every creature that ever lived on Earth. But sometimes, just sometimes, you get buried fast enough that the decomposers can't get to you. The soft parts still go. The organs, the skin, the eyeballs, all gone. But the hard parts, the bones, the teeth, the shells, those stick around. And over thousands of years, something genuinely insane starts to happen. Water seeps through the sediment. That water is carrying dissolved minerals. And those minerals, slowly, molecule by molecule, replace the original bone material. The shape stays. The structure stays. But now, it's made of stone. You just became a fossil. Congratulations. You are immortal. In the worst possible way. And that process, permineralization, is basically how most fossils form. It's slow. It's rare. It requires a very specific set of conditions. Which is why the fossil record is incomplete. Which is why paleontologists are always discovering new species. Because for every creature that became a fossil, there are thousands that just vanished. Silently. Without leaving anything behind. That's the first gut punch of paleontology, the fact that we're working with an insanely tiny fraction of what actually existed. And yet, somehow, what we found is enough to tell an absolutely wild story. But, okay. You found a fossil. Great. You've got a rock shaped like a bone. Now what? N? How do you know if it's 5,000 years old or 500 million years old? N? You can't exactly check a timestamp. This is where it gets clever. Really clever. Everything alive is made of atoms. And some of those atoms are unstable. They're radioactive, and not in the glowing green spider bite kind of way. In the quietly, predictably falling apart over time kind of way. And here's the key word. Predictably. Take carbon-14. It forms in the atmosphere, gets absorbed by living things, and when something dies, it stops absorbing it. From that point on, the carbon-14 in the body starts decaying, converting into nitrogen at a rate so steady and so reliable that scientists can measure how much carbon-14 is left and calculate almost exactly how long ago the creature died. That's radiocarbon dating. And it works beautifully for stuff that's up to about 50,000 years old. But wait, what about dinosaurs? And they're way older than 50,000 years. Carbon-14 decays too fast for that. So what do you use? And you use something that decays slower. Way slower. Uranium lead dating. Potassium argon dating. These isotopes take hundreds of millions of years to decay, which means they're perfect for dating ancient rock layers. You find the rock layer your fossil is sitting in. You date the rock. You now know how old your fossil is. It's like if you found a letter with no date on it, but you knew the envelope was printed in 1987. The letter's from 1987. Same logic. Different isotope. Alright? So now you've got a fossil, you know how old it is. And you're starting to piece together what this creature looked like. And this is where paleontology stops being chemistry and starts being something closer to art, but art with rules. Strict, evidence-based rules. When scientists find a skeleton, they're not just cataloging bones. They're reading them. Every bone is a sentence. Every scar, every groove, every weird bumpy ridge tells you something about how the animal moved, what it ate, how old it was when it died, whether it got injured, and whether it fought something else. The femur angle tells you how it walked. The shape of the teeth tells you if it was a predator or a plant eater. Attachment points on bones show where muscles were. And muscle mass tells you how the animal moved. From one skeleton, a good paleontologist can reconstruct an entire lifestyle. That's not guessing. That's reading a language written in bone. So let's talk about some of what we've learned. Because the picture of prehistoric life that science has built up over the last 200 years is so much weirder and cooler than anything you've seen in a movie. Wah! Here's the one that tends to break people's brains. Velociraptors were not the terrifying, human-sized killing machines from Jurassic Park. They were the size of a large turkey. They had feathers. They probably looked closer to a really aggressive, scaled-down ostrich than to the monsters stalking through a kitchen. The actual animal that inspired the movie version of the Velociraptor was Deinonychus, bigger, but still not 6 feet tall. And they almost certainly had feathers because they were, taxonomically, incredibly close to birds. In fact, and this is the plot twist that still messes paleontologists up, birds are dinosaurs. Not descended from dinosaurs. They are dinosaurs. Avian dinosaurs. When you see a pigeon on a sidewalk looking mildly confused, you're looking at a living dinosaur. The lineage never ended. It just got wings and got weird. Okay, but let's zoom out from velociraptors for a second, because as cool as they are, they're not even close to the most extreme creatures paleontology has found. Meet Patagotitan majorum. It's a sauropod, the long neck category of dinosaur. And this thing was roughly 37 meters long, and weighed somewhere around 70 tons. For reference, a school bus is about 12 meters long. Patagotitan was 3 school buses long and outweighed an entire herd of elephants. Its femur, just the thigh bone, was taller than most adult humans. Wow. And here's the genuinely mind-bending part. This animal was warm-blooded. It had a fast metabolism. Its heart had to pump blood 12 meters up its neck to reach its brain. Scientists estimate its heart may have weighed over a ton. Just the heart. 1 ton. Just to keep this animal alive. Pause on that for a second. A 1-ton heart. An animal so big that the word big becomes meaningless. An animal that breathed the same air, walked the same earth, looked up at the same sky as us, and we only know it existed because it left bones in Argentinian rock. That's the moment. Right there. That's the moment where paleontology stops being a science class and starts being something close to philosophy. Because the sheer scale of life that has existed on this planet, the variety, the extremity, the absolute biological creativity of evolution across 500 million years, is so far beyond what our daily experience gives us any reference for, that it almost doesn't feel real. But it is real. It happened. On this planet. In the ground beneath our feet. And evolution built all of it. Slowly. Blindly. Without a plan. Just the relentless pressure of, can you survive? Can you reproduce? N! If yes, carry on. If no, you're done. Generation after generation after generation. A billion tiny experiments running simultaneously across every environment on Earth for hundreds of millions of years. And what do you get? You get everything from a bacterium to a blue whale, from a mayfly to a Patagotitan, from a fern to a redwood tree, from Velociraptors to pigeons. The same basic process, the same logic, wildly different outputs. And here's the thing that actually connects paleontology to every other science. The rules of evolution are the same rules as the rules of physics. Natural selection is thermodynamics applied to biology. Systems move towards stability. Energy gets distributed. What works persists. What doesn't disappears. The universe's tendency toward equilibrium shows up in bones just as clearly as it shows up in heat equations. Two completely different fields. Same underlying logic. In disguise. So here's where we circle back to that really bad Tuesday. 66 million years ago, the dinosaurs had been running this planet for about 165 million years. To put that in perspective, humans have been around for roughly 300,000 years. The dinosaurs had us beat by a factor of more than 500. They weren't a failed experiment. They were one of the most spectacularly successful groups of animals in Earth's entire history. And then a rock showed up. A rock roughly 10 to 15 kilometers across, about the size of a small city, traveling at somewhere between 20 and 30 kilometers per second, hit what is now the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear bombs going off simultaneously. The explosion vaporized everything within hundreds of kilometers instantly. The shockwave was felt globally. Massive wildfires started across entire continents. Then, and this is the part that really finished things off, all that vaporized rock and debris shot into the atmosphere and blocked the sun. For years, no sunlight means no photosynthesis. No photosynthesis means plants die. Plants die, herbivores starve. Herbivores die, carnivores starve. The food chain collapses from the bottom up. And the bigger you are, the more food you need, and the faster you die. The non-avian dinosaurs, the big ones, the iconic ones, were gone within tens of thousands of years. Which sounds like a long time, but in geological terms, it's nothing. It's a blink. The evidence for this event is everywhere. Literally everywhere on Earth. There's a thin layer of clay in the rock record that shows up at exactly 66 million years ago on every continent, in every ocean. It's called the KPG boundary, the line between the Cretaceous and the Paleogene periods. And that clay layer is packed with iridium, a metal that's rare on Earth but common in asteroids. Find the iridium layer, you've found the impact. That layer is the crime scene tape around the whole planet. And the crater, the Chicxulub crater, is still there, buried under the Gulf of Mexico and the Yucatan, nearly 200 kilometers across. Still detectable with modern imaging. You can find the scar left by the asteroid that ended the Mesozoic era. It's just underwater, and slightly covered by 66 million years of new rock. Now here's the part of the story that usually gets left out. The asteroid didn't just end things. It also started something. Because when the dust settled, literally, the survivors inherited a world of open ecological niches. No more giant predators. No more massive herbivores hogging all the food. The small, furry, warm-blooded mammals that had been hiding under rocks and in burrows for millions of years suddenly had an entire empty world to expand into. One of those mammals, after about 66 million years of evolution, is you. Reading this, or watching this, I guess. The extinction that ended the dinosaurs is the reason mammals diversified so explosively. It's the reason primates existed. It's the reason humans existed. We are, in a very literal sense, a consequence of that asteroid. So when you feel bad about Jurassic Park's dinosaurs getting destroyed, remember, you only exist because that happened. And that's the story paleontology tells. Not just a list of cool extinct animals, but a continuous 500 million year narrative of life adapting, exploding in diversity, getting wiped out, adapting again, exploding again. 5 mass extinctions. 5 recoveries. And every single time, the survivors went on to build something weirder and more complex than what came before. We are, right now, living in the aftermath of the 5th mass extinction. On a planet with a 4.5 billion year history, in a universe that is 13.8 billion years old. And we've only been here for about 300,000 of those years. The bones in the ground are a record of everything that came before. And paleontology is the act of reading that record slowly, carefully, one rock at a time, and asking, what was alive here? N. How did it work? N. What killed it? Eh? Which brings us to the question nobody has actually answered yet. We know the asteroid hit. We know the timeline. We know the chemistry. But we still don't fully understand how life recovered so fast. The Cambrian explosion, the sudden appearance of almost every major animal body plan 540 million years ago, still doesn't have a clean explanation. Why then? Why so suddenly? Why so much variety all at once? And we have ideas. We have hypotheses. But we don't have an answer. Which means paleontology isn't a finished book. It's a book with most of the pages still blank. And somewhere, right now, there's a rock in the ground with a fossil inside it that nobody has found yet. An animal that lived and died before a single human being ever walked this earth. Just waiting.